Okay, very good. So welcome everybody. Those of you who are here today, I'm very glad you could attend. Our speaker today is Zohar Komargodski from the Simon Center for Geometry and Physics. Zohar is an expert in quantum field theory in general, and will be talking to us about his recent paper on giant vortices and the Regge limit. Thank you, Zohar.
Thank you very much, guys. Thanks for coming on Friday afternoon. Yeah. So this will be about the paper with Gabriel Cuomo, that appeared just recently. I'll start with some introduction to the subject and then get a little bit into the details. Maybe not enough details to satisfy Jeff, but we can talk later about more details if needed. So also, please stop me if there is any remark or comment or a question anytime would be nice. Otherwise, I'll just speak incessantly for an hour, and that would not be fun. So, of course, the motivation is that, in particular, there are strongly coupled many body systems. But in particular, there are also non-trivial strongly coupled fixed points of the renormalization group. Those are the conformal filters. And they are, since quantum field theory is essentially like calculus in physics, and it appears everywhere in all the branches of physics, the problem of understanding non-trivial fixed points is important in many different fields, ranging from statistical physics to condensed matter to high energy physics. So what people have been doing for, it's probably fair to say, almost 5 decades now, is that they've developed a very good understanding of local operators. So operators that are at a point in space-time at a fixed point. So we know that operators at a fixed, local operators are characterized by their scaling dimension, which is going to be denoted by delta, and by their spin. If there is a global U1 symmetry, you could also add the charge Q, which I'll do later. And we know that what's important are the correlation functions at the fixed point. And the correlation functions are characterized by the OPE coefficients, which is an infinite by infinite by infinite matrix, which is not known, of course, in any sufficiently interesting example, but it exists. And people have, over the last 5 decades or so, people have convinced themselves that this data, namely the space of local operators and their OPE coefficients, is more or less sufficient to characterize correlation functions of local operators. So the main idea here, which also, like 15 years ago or so, this idea has also become something that you can do in numerics. So people now know how to attack the problem of finding this data via numerics, and it's a useful numerical algorithm for operators which are sufficiently simple, so their delta and J are small enough. So there is the main equation that constrains this data, the Cijks and the scaling dimensions and the spin, is the fact that the operator product has to be associative, and it leads to a very non-trivial, non-linear equation for the deltas and the C's. And yeah, the progress in this paper is that they've put it on the computer and managed to generate some useful insights into the space of possible solutions of this associativity equation. I should say that this is useful only for light operators at the moment, so the operators with small scaling dimensions. So in parallel to this numerical progress, which is very nice, there has been progress on understanding analytical properties of conformal field theories. But analytically, it's very difficult to say something about light operators. However, heavy operators with scaling dimension, which is much, much bigger than 1, are more amenable to analytic tools that we can use effective field theory or even the eigenstate normalization hypothesis and these kind of things. So heavy operators are a little bit more amenable to analytical control, but of course, experimentally, they're less accessible. You have to do much more. You'll see some experimental data soon, but you'll have to do some refined experimental computations or Monte Carlo computations to access heavy operators. Usually, as is known from the days of Wilson, what's important around the fixed point and its phase diagram are the low-lying operators, not the heavy operators. So while the heavy operators are more easy to understand analytically, they're much more difficult to measure. So here, I'm not going to talk about the generic question about heavy operators. That has to do with black holes and so on. Instead, I'll talk about a very concrete question about heavy operators, which is the lowest operator with some given charge Q and some given spin J. We'll try to understand what can we say in general about the lowest operator in a fixed charge sector. Okay, this is the main question. And what is going to be the main tool? Well, the scaling dimension is an abstract quantity and we don't have much physical intuition for it. But if we use the state operator correspondence, which maps local operators in space-time to states on an auxiliary sphere, quantum states, quantum eigenstates on an auxiliary sphere, then operators with a very large scaling dimension on the left-hand side map to eigenstates on this auxiliary sphere with large energy density or large charge density. And the question of finding the lowest operator maps to the question of finding the ground state of the theory on this auxiliary sphere in the presence of some fixed charge density or fixed angular momentum. So finding the ground state of a quantum system is a little bit more easy as a conceptual question than to answer this question in the abstract, because we have some intuition. So are there any questions about the introduction and what are we aiming to do? Okay. Also stop me at any point if there is something that comes up. So this is the last topic is something I'm not going to talk about. This is the question of what can we say about generic heavy operators, which are not the ground states at a given charge sector. Of course, this has to do with hydrodynamics and ETH, and black holes and these kind of things. It's less concrete and it's more, I mean, it's much less concrete, much less concrete stuff is known. I'll first review what's known about the ground state at a given spin. And then I'll review what's known about the ground state at a given large charge. And then we'll try to draw a phase diagram as a function of J and Q for the ground state of the quantum system. So if we could make an experiment on this auxiliary sphere and find the ground state at 0 temperature with a given chemical potential, then this should agree with what I'm going to say in this talk, hopefully. So let me begin with the large spin. You can ask, what are the lightest operators of a given spin? The spin could be very large. So if you have some intuition from ADS-CFT or this kind of thing, you might think the answer is a rotating black hole, but that answer is incorrect. So let me tell you what is the correct answer for the ground state at a given large spin. So first, there is a very important fact to know that is true in any conformal filter, which is that if you take any local operator and you put lots of derivatives and then another local operator at the same point, there is very little renormalization for the scaling dimension of this operator. So this is like, sometimes people call it asymptotic freedom at large angular momentum, or asymptotic freedom at small angular separation. So in QCD, we have asymptotic freedom at large energies or small distances. Here we have asymptotic freedom at small angles, you could say. So operators with lots of derivatives receive very little correction to their scaling dimension. So here's the formula. The scaling dimension of this particular phi dj phi operator with many derivatives here is linear in J with coefficient exactly 1, because you have J derivatives here. Then you have 2 times the dimension of this phi, which I'll sometimes call partons. So these little phi's, I'll sometimes refer to them as partons. 2 times delta phi. And then there are corrections because it's not exactly free. After all, it's an interacting conformal theory, but the corrections go like an inverse power of j. And the exponent of this inverse power is going to be 1 in this talk, because it's 1 in all the interesting examples that we'll cover today. So think about tau min as 1. And this is some coefficient that is actually exactly known. You can obtain it by an analog of the one-loop computation of the beta function in QCD. So what is the picture for this ground state? It's very different from a black hole. You can think about it on this auxiliary sphere as two particles that are rotating around each other at a very large angular velocity. Or in ADS, you can think about it as two particles that are rotating far from the center of ADS. So it's a similar picture. And that is the ground state at given J, not a black hole, at least for large enough J. So this is a prediction for the large spin limit, for the ground state at the large spin limit. It's just about partons that are rotating around each other. Let's see if this agrees with experiment. Well, the experiment here is going to be some numerical experiment, not a real experiment yet. So what do we see here? Tau is delta minus J. So if we go back to the previous slide and we subtract J from both sides, we see that delta minus J would be 1 over J plus an asymptotic constant, which is 2 delta. And indeed, if you look at the O2 Wilson-Fisher fixed point, this is the O2 Wilson-Fisher fixed point in 2 + 1 dimensions, which is a simple CFT with global U1 symmetry. You see that indeed all the curves nicely asymptote to this asymptotic constant. And apparently the only thing that's a little different is the coefficient here, the number, which you can compute from some theory and match to the data very nicely.
So what is L on that in that graph?
Oh, I'm sorry. I just actually took a graph from Liu, Meltzer, Poland, Simons, Duffin, and for them L was J.
Okay.
Okay. So this is the ground state at large spin. Truly large spin. Although I should say that this prediction here seems to agree very well with the data, even at spin which is not so large. You see that they go down to 5, 10, and these curves are the theoretical curves, the blue, red, and yellow, and they agree very well with the data, even at spin which is not so large. This is like the magic of effective field theory, that it sometimes agrees with the answer, even a little bit away from the regime of validity. Okay, so this is the story of the ground state of at large spin. But now let me tell you a more complicated story. What if you fix Q? What is the ground state at large spin, but at some fixed charge Q? So now it's not enough to have two. Well, you could have two partons, each carrying charge Q over 2, and they would be rotating around each other. That would be a very good guess. But actually, that's not the ground state. You can lower the energy a little bit if you break up the partons into Q partons, and they start spinning around the sphere. So if you want to write it as a local operator, you're going to have Q partons, each of charge 1, and then J derivatives sprinkled around in some random way. And you see that there is now entropy, because you can sprinkle around the derivatives pretty much any way you want. And to leading order, it would not change the scaling dimension. So the picture for this state is that you have Q partons orbiting the sphere, or if you think about it in ADS, this would be Q partons orbiting the center of ADS. And there is a huge degeneracy, because you can change the relative distances without paying any fine at leading order. So there are tiny corrections that go like the charge cubed over the spin. So this is tiny when the spin is the largest parameter. And those tiny corrections should be sensitive to changing this little separation here. But actually, this wasn't yet computed. Nobody knows exactly how this correction looks like and how this huge degeneracy is lifted. So what is this degeneracy? It's just a way of how do you sprinkle J derivatives among Q partons. And it goes like an exponential of Q. So if Q is like 10, it's not such a huge degeneracy. If Q is 100, it begins to be interesting. And this is, of course, this picture of Q partons rotating around the center of ADS, or the center of this auxiliary sphere, is the ground state at some fixed Q, but very large J. Okay, these things so far we know for sure. The only thing here that is an open problem is to understand how this huge entropy is resolved. Like, how is this degeneracy lifted? This requires a computation of this correction, which was not yet performed. It's a nice open question to think about how to do it. Okay. We see something interesting in this picture so far. We see that when the spin is not so large, but it begins to be of order Q squared, this whole picture with the spinning partons might break down. Why? If you consider this formula and you put J equals Q squared, then this becomes of order Q, which starts competing with this. And so we lose our faith in the fact that this might be the true ground state. Maybe the true ground state is something else. So J equals Q squared is an important scale in the problem because we see this interaction between the partons might change the qualitative picture when the spin is of order Q squared. So that begins to be interesting because we have to guess the new ground state. So it's important that this interaction here that might change the ground state of the system eventually when J is of order Q squared is attractive. So we don't exactly know the shape, the form of this interaction, but we know that it is attractive because we computed a certain exchange diagram. And this is interesting, so let me just make a small comment about it. In the ADS picture, you have particles rotating around the center, and to leading order, they're free because they're very far from the center of ADS and therefore very far from each other. And so the interaction between them is due to the electric repulsion between the partons. The partons are all carry the same charge, so they're all in the ADS language, they're repelling each other with Coulomb repulsion, but they're also attracting each other gravitationally. So to understand if these partons are attracting or repelling each other, that might give you some clue about what happens when J is Q squared. You have to compare the exchange of the graviton and the exchange of the Coulomb force. And unlike this GUI gravity conjecture stuff, where people say that gravity is the weakest force, at least in the O2 model, it's not true. Actually, gravity wins. And the partons are attracting each other. So you basically have a bunch of particles that begin to attract each other. And when the spin is not too large, they're not so far from each other. And this state might collapse to a new ground state. So you might see hints of that maybe there is a Bose-Einstein condensate and some kind of vortex forms, because they're going to keep spinning and maybe they'll just become like a continuum that is spinning. Okay, so that might be your intuition for what happens when J is lowered below the scale Q squared. Okay, so gravity wins in this model. In fact, I think gravity wins in probably all models that I've checked. So it's the opposite from the weak gravity conjecture. Okay, so we see that at large J, the answer is no. When J hits Q squared, there might be a new interesting ground state. And now I'm going to review what happens at large charge, but small spin, and then we'll try to build the whole phase diagram. Are there any questions about large spin?
No, not a question about large spin, but maybe just I'm trying to reconcile it with my intuition for the problem. So if I think about what happens with, let's say, vortices on flat space, let's say vortices in some finite domain, but a flat finite domain. Although I think there's a similar statement for what happens if you put like Nielsen-Olesen vortices on a sphere, on a two-sphere. Any higher winding number vortex is not the ground state. They will degenerate into Q equals 1 vortices that will then repel each other and form a lattice.
First
Right?
of all, I have not spoken about vortices yet.
No,
This
no,
part,
sure. But I'm trying to understand your Parton picture, and
the
the
partons are
language
not
sounds
vortices.
similar.
The partons are not vortices. They're not vortices of us. There is no superfluid yet. This is just, these partons are like the
Are they
states.
neutral?
No,
Are they charged? They're charged, right?
They're charged. In the ADS picture, they're charged, yes.
Oh,
And
okay, okay.
also in the CFT, they're charged. So these partons are not vortices. You think about them the following way. You can think about them like delta phi is some operator in the CFT with charge 1. So there is a corresponding state in the CFT. And you can think about making some kind of wave packet out of this state by smearing the local operator in an appropriate way. So you can think about these partons as just like the wave, like localized versions of the state that corresponds to this phi. So it has charge 1, but it's not a vortex yet. However, this story does have an analog of exactly what you said, that it's beneficial to break the vortices into pieces, into constituents with vorticity 1. And this is that story, that it's more beneficial, if you do the computations here, it's more beneficial to have Q partons rotating rather than 2 partons of charge Q over 2 rotating. It turns out to be more beneficial energetically to break up the partons into fundamental charge partons.
Okay, I see.
Okay, let's keep going. So now I'm going to change a little bit the subject. We're not going to talk about large spin anymore. I'm going to tell you what is believed to be true about the large charge limit of conformal field theory. So this is a little bit more, this is a little less rigorous in the sense that everything I've said so far can be proven. But what is the large charge limit is a little bit more speculative, but by now there is convincing numerical evidence that it's true. I forgot to add, I can show you guys later, but there was a recent simulation by Su and Rong that more or less confirms this picture that I'm going to advocate. So the charge density, so now we are asking what is the ground state of the conformal theory on this auxiliary sphere, but with some large charge Q. So if we have charge Q, we have charge density mu squared. And that defines a new scale compared to the radius of the sphere, which is 1 over r. So if the charge is large, there is some scale separation. So the charge density is much above the radius of the sphere, and you can imagine an effective field theory. Now, in condensed matter theory, if you fix the charge density and you ask what is the ground state, people have found many possible phases of matter. Perhaps the 2 most famous phases that can appear are the Fermi surface, which is just a bunch of, it describes basically a bunch of free fermions at the correct density, or a broken U1 symmetry, which is a superfluid. And for some reason that is not currently clear, as far as I know, in all the models that people have looked at, the superfluid is the right answer. There are some intermediate regimes where a Fermi surface appears, but it seems to be always eventually unstable to perturbations. And the superfluid is the right ground state. So let's analyze this ground state at large charge. You can think about the superfluid as a statement about symmetry breaking, that we're looking at the ground state of the system at large charge. So we have time translations and U1, and this ground state is going to preserve the diagonal of time translations and U1. So we have a Goldstone mode, which is pi, it's the sound mode. And we have a superfluid density. And we have a gap. So the effective action, this is the effective action for a superfluid on the sphere. It looks bizarre. There is a kinetic term, which is of a cubic kinetic term, which looks very bizarre. And you might think it's a very sick effective field theory. But remember, we're not using it around the origin. We have an expansion around finite density. So we're plugging in this profile for chi, and treat pi as small fluctuations. So therefore, we can use this weird non-analytic kinetic term because we're expanding around a background with constant density. So what do we find? We find that the scaling dimension for an operator with very large charge Q, but no spin, is basically Q to the power 3/2. And people have used the effective filter to compute the next correction, and also the next to next correction. And this fits the data very well, some Monte Carlo data. So we believe that this is the right answer. This is the answer for the large charge limit. And if you expand in fluctuations, you see that the fluctuations are phonons, they're usual superfluid sound modes, and they're moving at the speed, which is 1/√2 times the speed of light. So the speed is 1/√2 times the speed of light. And this is the dispersion relation of these phonons. So a phonon of spin J on the sphere would cost you this amount of energy. And there is a Fock space of phonons, and they are non-interacting to leading order. The interaction between the phonons is suppressed by this UV scale mu, which is the charge density. And that's why effective filter is valid, because the phonons are almost free. Okay, so this is the picture for what we believe are the ground state at large Q. Again, you might thought that the answer is a black hole, a charged black hole, but the answer is not a charged black hole. It's a superfluid. And while this formula looks similar to a black hole, Q to the 3/2 is also what you get from a charged black hole. This is the effective filter is not that of a black hole. It's maybe more like a boson star or something like that. Okay. So we can also now discuss what happens if we take the superfluid and give it a little bit of a spin. Then we get sound modes, and this is the scaling dimension, and that's what people see in numerics. So by now, people have verified not only that the ground state is Q to the 3/2, but also that the spin dependence for very small spin is that given by the sound modes of a superfluid. So there is very convincing evidence that what I'm telling you is the right answer. And now we have a pretty good answer at very large spin with these partons, and a very nice answer at small spin, which is this superfluid with some phonons. But the phonon description breaks down at square root of Q. You cannot trust this formula when J exceeds square root of Q, for the reason that, as I said, the phonons have some self-interactions, and you lose control if you put too many phonons. So it doesn't allow you to excite too many phonons, and you have to now go beyond that regime. And as Jeff said, when you take a superfluid and spin it beyond what the sound modes allow you, you start generating vortices. And these are some nice pictures of experiments where vortices were observed. So we're now going to add vortices to the superfluid, and then hopefully at the end make contact with the picture of partons. So at the beginning, there would be just a few vortices, and then there would be a lattice of vortices, which is known as the Abrikosov lattice. Are there any questions about this? Then I'll just tell you a little bit about the physics of vortices in the superfluid, and then we'll keep going with building the phase diagram of the ground states of this model. Okay.
I have some questions, but I think that's the direction you're going.
Yeah, go ask, and then I'll see if I'm going to actually get to it.
I just wanted to find out if you know what happens as you continuously turn up the angular momentum of the superfluid. If you know the details of how you go from, let's say, the picture on how you go from left to right in these pictures.
I think it's an open question.
Okay, that's right. Okay, so
people know how to answer it with numerics in Gross-Pitayevsky,
yeah,
or Thomas Fermi theory.
Mm-hmm.
But I don't believe anybody knows if it's a second order transition, first order transition. Even in Gross-Pitayevsky, I believe it's mostly numerics. people know very little about the nature of these transitions. Now you see,
Right.
it's very interesting because you have large quantum numbers. So even though the model is in compact space, it's on an auxiliary sphere in our case. Because you have large quantum numbers, the question of what is the order of the phase transition is well defined. So it actually makes complete sense to ask, what is the order of the phase transition to form a lattice? Or what is the order of the phase transition that I'll talk about later? But I believe the answers are not known.
Okay, thanks.
So how do you think about vortices in a superfluid? Actually, vortices in a real fluid are also behaving like this, except that they are dissipating. Vortices in a superfluid are not dissipating, so it's a little bit easier. A vortex in a superfluid moves like a particle moves like a charged particle moves in a constant magnetic field. So you can think about a superfluid as in this language as providing constant magnetic field for the vortices. And the vortices are like charged particles. So charged particles experience electric repulsion or attraction. And because they're moving in a constant magnetic field, they also experience Lorentz force. And you can ask, what is the size of the magnetic field? And we computed it, and it turns out to be exactly Q. So Q, the integer Q, is what provides the number of flux units through the sphere. A very important fact about charged particles moving around the magnetic field is probably what was known from the time of Dirac, which is that they acquire a very large spin. So you remember this classic fact that the particle moving in a magnetic field, so a boson moving in a magnetic field could become a fermion. It acquires half-integer angular momentum. That's called 't Hooft-Hasenfratz sometimes, or Goldhaber mechanism. If you have a lot of magnetic field, then a particle like a vortex could acquire a very large spin. So this is the spin of a vortex. It just points to the location of the vortex, and it has Q/2 units of spin, and little q is the number of vorticity, is the vorticity number. So first, when you start spinning the sphere, a vortex anti-vortex appears. They would be placed on some random locations on the sphere, and as you keep increasing the spin, they drift to the north and south pole because that's the way to maximize the spin. And that leads you to a universal prediction for the ground state of the system in this domain for the angular momentum. Between square root of q and q, you just have a vortex, anti-vortex, and the north and south pole. There is some interesting logarithmic correction to the scaling dimension. This has not been observed experimentally yet, or in Monte Carlo. So first, we have just phonons. First, we have just a superfluid. Then we have phonons. And now we have a vortex, anti-vortex, and the north and south pole. As you keep increasing the angular momentum, as we have seen from those pictures in the trap, the number of vortices proliferates, and eventually they form some sort of lattice where you can define an average notion of the number of vortices. So when you keep increasing the spin, indeed, we found a phase where there is some density of vortices, and they lead to some energy for the ground state. And this description is valid all the way to q to the power 3/2. So this picture is like a lattice of vortices that's just rotating with the sphere, with the angular velocity, some angular velocity which is determined by the angular momentum, but the configuration is rotating in such a way that it looks like a rigid body. So you should think about these vortices and think about them on a sphere, and they will be rotating together with the sphere. So that's the next phase. And it is believed that this phase of this Abrikosov lattice, or the rigid body phase, is correct all the way to the supersonic limit. So when you start spinning the sphere with velocity that exceeds 1/√2, then somehow this should break down. But it's not exactly known how. So in the paper, we have an appendix where we wrote the equations, and it seems actually promising. We found a new phase, a new solution to those equations numerically, exactly when the speed becomes the speed of sound. So apparently, probably there is some phase transition, and this rigid body phase becomes unstable when the angular momentum hits q to the power 3/2. And the velocity is exactly the supersonic velocity, the speed of sound, sorry. So what is the summary? I'll stop for a second now. The summary is that it seems like there is a good guess for very large spin in terms of these partons and Regge theory. And for angular momentum below q to the 3/2, the picture of the ground state of the system is a superfluid, possibly with vortices. And eventually you get a lattice of vortices. And the lattice of vortices should become unstable when you reach the speed of sound. This is the summary of what I said so far. Are there any questions about this? Let me see.
No.
Yeah, let's move on. So there is a missing ingredient. There is a missing piece in the puzzle, you see? Because what is the ground state between q to the 3/2 and q squared? We cannot use the rigid body and we cannot use the partons, the Regge partons anymore. So of course, you guys probably know, recently people found a new phase for a rotating superfluid in a trap, which is called the giant vortex. It's a very interesting new phase where the superfluid does not extend throughout the trap, but it's basically localized to a strip. And only in that strip, there is some superfluid density. And in the blue regions, it's like gapped. There is nothing there. So it's now believed that there is a growing amount of work by, you can look at this paper, for instance, and citations to this paper, of also mathematicians trying to show that this is the correct ground state when the angular momentum exceeds the speed of sound. It's an interesting problem to understand how this transition takes place, because you open a gap in the superfluid. And it's interesting to know if this gap opens like in matrix models via a second order transition, like in the famous unitary matrix models of Gross and, oh my God, I forgot the other author on that paper. Or maybe this gap opens via first order transition, like in complex matrix models. So this is a good open question to think about. But either way, inspired by these experiments, we just made the obvious step and said, let's look for a solution like this on this auxiliary sphere. Let me just show you the solution. I'll get back to the phase diagram afterwards. So the solution is a vortex, is a superfluid, chunk of superfluid rotating around the equator. A small, the green strip here, the small strip here, it's like a boundary layer. And the physics of the boundary layer is complicated. Also, for the giant vortex people that do it in an ion trap, the physics of the boundary layer is something that needs to be worked out. They haven't actually worked it out yet. So we actually found a solution to this. Solution to what? Let me just explain again. We went all the way back to the effective action for the superfluid. And instead of expanding around this constant density solution, we found a new solution, which mimics the physics of the giant vortex. This is our solution. And it leads to superfluid density that is bound to a strip. And you can compute all the quantum numbers of this solution. It has some angular momentum, some charge, so on and so forth. But the qualitative features are exactly like in the experiment. There is a gap in the blue region, some boundary layer theory in the green region, and in the red region, you have a superfluid that's spinning with no vortices. And for the effective field theory to make sense, you need to require that the boundary region is not too big. Otherwise, the contributions of the boundary region would destroy everything I'm saying. And you need to require that the red region is sufficiently big compared to the cutoff. So imposing these two conditions, we miraculously landed exactly where we needed. So we had a hole in listing all the phases. We couldn't find the phase between q to the 3/2 and q squared. But once we found the solution and imposed the validity conditions for the effective field theory, namely that the green strip is not too big and the red strip is not too small, we found exactly the right answer. So it exactly fits into the spec. So this is our claim for the phase diagram. So we have Regge theory, which is the universal large spin effective theory, giant vortex, and then superfluid with vortices, which is these three phases are superfluid with vortices. So it really works like a gem. It fits exactly the missing region. So when the angular momentum is close to q to the 3/2, the gap, namely the blue region, becomes very small. And we're getting closer and closer to the rigid body, presumably. The rigid body or the abrikosov lattice. When J is of order q squared, the red region becomes narrow. And presumably the giant vortex just somehow collapses to these partons. So you can maybe imagine that when the red region is very narrow and it's spinning very fast, it somehow breaks up into q partons. Maybe it's not difficult to imagine, but of course nobody showed it. Okay, so we computed the energy of the giant vortex, and lo and behold, it's exactly linear in J, like in Regge theory. So we went all the way from q to the 3/2 to linear in J, and the slope is exactly 1. So we matched exactly with Regge theory. And the most bizarre thing about this giant vortex, which I believe is also valid for the experiments, is that the fluctuations are chiral. So we've quantized the fluctuations around the giant vortex. You get a chiral theory, very similar to the Latinger liquid, like the compact boson theory. But some differences is that there are excitations with an arbitrary integer frequency, including negative or positive. So there is an infinite degeneracy. That infinite degeneracy is very similar to the degeneracy in the theory of partons. It's split by some small corrections, but those corrections need to be computed carefully. So there is an approximate infinite degeneracy. The theory is chiral, and the speed of sound is now not 1/√2. It's exactly the speed of light. So that's why this giant vortex is the magical solution to the previous concerns with the supersonic configurations, because now the speed of sound in this red region is the speed of light. It's not it's the same as the speed of light. So you can actually spin this thing ad infinitum until it becomes too narrow. So that's how we avoided a disaster when the rotation speed is exactly the speed of sound. Okay, so there are chiral excitations moving at the speed of light, and there is an approximate infinite degeneracy. And we believe this is exactly true also for the giant vortex in the BEC condensates that people observe in the lab. We'll have to see if this is true. And if you want to see the effective theory for the fluctuations, it's this weird chiral theory, which looks very non-standard with a funny kinetic term. And we have a section explaining how to quantize this theory. There are some sicknesses in the quantization of this theory, but you can do it. It's an unorthodox kinetic term. Okay, let me just mention some open questions. It would be very nice to extend this to 4 dimensions, an abrikosov lattice of strings rather than of vortices, and to see what are the corresponding phases. Now, this goes back to the question that we discussed at the beginning of what is the nature of all these transitions. This is not known. In particular, what is the nature of the transition from the rigid body to the giant vortex? Also, while I gave you a phase diagram, it's probably not completely true that these are all the phases. Like, there could be intermediate phases between the abrikosov lattice and the 2 vortex phase. Well, it's possible that there are more phases. It's not completely known what are the phases. Also, it will be interesting to understand how the partons collapse into the giant vortex. So there is this attraction, which is the opposite of the weak gravity conjecture. And this attraction should lead to a condensate. And it will be interesting to see how that works. How do you get the giant vortex from particles in ADS, which collapse to a condensate? Boundary layer theory is an interesting problem, both for the experiment and for the theory. Like, you have to understand carefully the boundary conditions on the green layer and how they contribute, for instance, to this formula, the energy of the giant vortex. or how they contribute to the dispersion relation of the fluctuations. People have noted that some formulas of this giant vortex are very similar to non-supersymmetric extremal black holes. In particular, the delta equals J, and the spectrum of the fluctuations looks a little similar. So it would be nice to make contact with that subject. Okay, thank you very much. If there are more questions, I'm happy to discuss. I probably froze.
Sorry, Zohar. Can you hear me?
Yes,
can you
I
hear
can
me?
hear. Yes,
Okay.
I can hear.
Sorry, I lost you for a second.
Oh. I don't know if you could see what I was talking about for the last minute or two.
For the last like 30 seconds, you froze, but that was only on my side. I don't know if anybody else. No?
I just went through the open questions.
Okay. No, I got I got you up to gravitational collapse.
Okay,
then-
no, the last thing I said is that working out the boundary layer theory would be useful both for the experiment in trapped ions and also for the CFT applications, because the boundary layer has contributions to the ground state energy and to the dispersion relations, small corrections to the dispersion relations I mentioned. And the last thing was that people have noted that some of the things we find for the giant vortex are very similar to non-SUSY extremal black holes. So that is another direction I mentioned would be nice to explore. And probably at that point I froze or something.
Right. Just slightly below that, before that, but yeah, I don't know if anybody else, if it was for anybody else, but are there any questions?
Hi, Jeff. Oh, sorry.
Hi, Matibi. Go ahead.
Hello.
Hello. So I hear you mentioned that like the obviously you did mention that the boundary layer theory is not yet well understood, and that it gives small corrections to a number of quantities that you care about here. So I wonder that sort of kind of bound that you put on the size of the boundary layer, how much can you relax it before then the physics or whatever goes on in the boundary layer gives appreciable corrections to whatever quantities you care about. Is it so strong? Is it so strong a restriction, or can you sort of kind of?
Yeah, it's a great question. I have two comments about it. Even if the boundary layer is tiny, even if that region is very, very small, and you could think you could neglect it, it's still important. This small contribution is crucial, because otherwise there is infinite degeneracy. So the spectrum of fluctuations that you get from the bulk of the giant vortex has this very strange dispersion relation, which leads to an infinite degeneracy. It's the same infinite degeneracy that we saw in Regge theory, so we were very happy about it. It's not a bug, it's a feature. But it cannot be exactly infinite degenerate. Both in the large spin expansion, there were tiny corrections. And also here, there should be tiny corrections to this infinite degeneracy. And so I think the boundary layer contributions are crucial, even when this quantity is very small. So the size of the boundary layer is delta bar over delta. So this big thing is delta, and delta bar is the small green thing. Delta bar over delta is j over q squared to the power 2/3. So if you're in that domain, the boundary layer is small, but even if it's small, it's the leading contribution to something. Okay, so it would be important to get the contribution from the boundary straight, because it leads to small splittings in this infinite degeneracy. And there is corresponding small splittings in the infinite degeneracy in the Python region in Regge theory, and it would be nice to compare them. That wasn't done yet.
Oh, okay. So it's basically important for degeneracy lifting here.
Yes, it's the leading effect. It's the leading effect for the degeneracy lifting.
Oh,
So,
okay.
and it's the same for the, I'm completely convinced that even for the giant vortex that they saw in the lab, it's still chiral excitations and infinite degeneracy to first order with small gap. And I'm convinced that the same physics would be important for the giant vortex in the lab.
Oh, okay. I see. Thank you.
Thanks for the question.
So for the giant vortex in the lab, the gapped region is there's two gapped regions. Everything is blue, right? Is that correct?
Yes.
So when you say small gapped region, does that mean that the ring closes around the interior blue region, or?
Oh, okay. So if you start from the Abrikosov lattice, it is everywhere inside, let's say. Then at the beginning, you see this blue hole in the middle.
Mm-hmm.
So once the velocity of the Abrikosov lattice exceeds the speed of sound, presumably a small blue hole opens up. Small blue hole opens up. We don't know if it opens up continuously or via first order transition. And then as you keep spinning it further and further, the blue hole increases in size. Okay. And the giant vortex should be a good description, and as long as the red region is sufficiently big that effective field theory makes sense. But eventually also the red region would become very small. And then I think they'll find the partons, but they haven't reached that angular velocity yet.
Mm-hmm. In the actual lab experiment, this is done on a disk, or?
It's done in a trap, in a disk, yes. You can,
Okay.
it's a disk. The topology is a disk, but you cannot, like, there is some limit of how much you can extend because there is a trap.
Right. So that would presumably set the size of the disk.
Right. The sphere is another nice geometry because on the sphere it's just naturally compact. So
That's right. You wouldn't have to worry about any edge effects on the sphere, right? Do you know this Bradlow bound of vortices on a compact space?
what is it? Remind me, maybe I know it in a different name or
The total number of vortices is bounded
yeah,
by volume.
sure. Yeah.
Yeah.
So
Yeah, no, go ahead.
let me go back to. So this is the analog of the Abrikosov lattice. And this is the density of vortices. You can compute the total number of vortices by integrating the density of vortices. And you see vortices, the vortices spin around the sphere. They have no choice but to spin around the sphere.
Yeah.
Because they are repelling each other. So they need some kind of force that would stabilize the repulsion. And that force is given by the Lorentz force because they're moving in a magnetic field. So they have to spin together. The whole sphere has to spin together.
Yeah.
So the regime of validity of the Abrikosov lattice comes from the following fact. If there are so many vortices that their rotation velocity exceeds the speed of sound, presumably this configuration breaks down. So I would say the upper limit on the number of vortices comes from requiring that their velocity is below the speed of sound. I don't know if this is the same as the bound that you quoted, but that's the bound we believe is true.
Right. Yeah, I'm not sure either, but I mean, your argument for this bound makes sense, and the argument that
I should say the following. I should say something else in that regard. You can also try to get the bound in a different way. You can say that we have some we have some intuition about the size of a vortex, that it cannot be more than the cutoff scale, which is mu. in this in my notation. It's the size of the vortex, which cannot be smaller than mu, let's say. And vortices are incompressible. So you can try to put a bound on the number of vortices by saying that the total number of vortices cannot exceed the volume of the sphere divided by inverse mu, which is the inverse size of the vortex, okay?
Right. I think that's what I was talking about.
If you plug that formula in, you get exactly the same scaling. So both conditions happily agree that they happily give you q to the 3/2, both of them. So
Right.
the angular momentum is bounded by q to the 3/2 from both arguments. One is that the vortices are incompressible and they cannot be smaller than inverse mu. And the other is from the fact that they should not be spinning supersonically. Both give you the exact same bound.
Great. Thank you. Any other questions?
If not, then thank you so
If
much.
not, let's thank Zohar again. It was an excellent talk. Thank you very much.
Thank you for the opportunity.
Great.
Thank you. Bye-bye.
Bye.